You ever wonder how a car factory can put together thousands of parts with perfect precision over and over again without making a single mistake? Well, today on The Explainer, we're going to pull back the curtain on the invisible brain that makes our whole automated world tick. I mean, it's just this incredible dance of precision and speed, right? But behind what looks like magic, it's not a magician. It's a controller. And all those constant, repetitive, super high-speed tasks you see on an assembly line, yeah, those require a very, very special kind of digital brain. So that brain, that special computer, it's really the unsung hero of all industrial automation. And today, we're going to learn how to speak its language.
Okay, but to really get why this new brain was such a game changer, we've got to go back in time. Back to an era before software was running the show. Because trust me, automation back then looked and it sounded a whole lot different.
So I want you to imagine this. Forget computer screens. We're talking about an entire wall just covered in thousands of clicking, whirring, buzzing switches called relays. We're talking miles, and I mean miles of copper wire, all just to control one tiny part of an assembly line. Every single logical step, if this button is pressed, then that arm moves. That was a physical, hardwired connection. And yeah, as you can probably guess, this system was an absolute nightmare. These mechanical relays, they'd fail all the time. They were slow, and trying to find a single problem, it was like looking for one specific wire in this giant, tangled mess. But the real killer? When a car company wanted to roll out a new model, they couldn't just, upload new software. Nope, they had to rip the whole thing out and start from scratch. We're talking millions of dollars in downtime and labor. So this constant headache, especially for the American auto industry, well, it finally sparked a revolution. They basically put out a call to the world saying, we need a replacement, something that isn't hardwired, something flexible, reliable, and tough enough to actually survive on a factory floor. And the solution that came back was the Programmable Logic Controller, or PLC for short. Now, don't picture the computer on your desk. This thing was ruggedized, which is basically a fancy way of saying it was an armored computer. I mean, it was built like a tank to survive constant vibrations, crazy temperatures, and all the chaotic electrical noise of a factory, all while making decisions in just thousands of a second. And the origin story here is just fantastic. Seriously, this wasn't invented in some sterile lab. Back in 1968, General Motors literally just published a wish list for a standard machine controller. A little company called Bedford Associates decided to take on the challenge, and their 84th project, the 084, was the one that won. And that project was so successful, it spun off into a whole new company, Modicon, which, you guessed it, stands for Modular Digital Controller. All right, so now we have this amazing new box. But how do you tell it what to do, right? You couldn't just go out and hire a bunch of computer scientists for every single factory. The solution had to be a language that the electricians and technicians, the people already on the floor, could learn, and learn fast. And this is where the real genius comes in. The first PLCs used what you could call a bridge language. Instead of, complicated text-based code, they created something that looked and felt totally familiar to the electricians who already knew relay circuits inside and out. They called it ladder diagram, or ladder logic. And the name is just perfect, because it's designed to look exactly like the electrical schematics it was replacing. You've got two vertical rails on the sides. Think of that as your power source. And then you build your program with horizontal rungs of logic that go in between. Okay, so while ladder logic is still kind of the king just because it's so intuitive, the world of PLCs has gotten a lot bigger. Now there's a whole family of languages, and each one has its own strengths. On one end of the spectrum, you've got these super visual languages like ladder diagram and function block. They're awesome for just seeing the flow of logic. But on the other hand, you've got something called structured text, which looks a lot more like traditional computer code. You'd use that for the really heavy-duty math or complex data stuff, things that would be super clumsy to try and draw out in ladder logic. It's really all about using the right tool for the job. But of course, as PLCs just exploded in popularity, a whole new problem popped up. You had Allen Bradley, you had Siemens, you had Modicon, all these different companies building their own hardware and their own software. So we'd solved the wiring nightmare, but now we were creating this software Tower of Babel, where every brand of PLC was speaking its own unique dialect. So to fix this, industry leaders had to come together to create a common language, a global standard. The organization that really led this charge was PLC Open, which is a group that's totally independent of any one company. And their whole goal was to get all these different systems to just play nicely together. And the result was this thing called the IEC 611313 standard. You can think of it as the official rule book for PLC programming. It laid out a common foundation for things like data types and how programs are structured. But the most important part? It standardized those 5 languages we just talked about. This made sure that ladder logic on a Siemens PLC would look and feel pretty much the same as ladder logic on an Allen Bradley PLC. And the impact of this, it was huge. All of a sudden, a programmer's skills were portable. You weren't just an Allen Bradley programmer anymore. Companies could start reusing code instead of reinventing the wheel on every single project, which, as you can imagine, saved a ton of time and money and cut down on errors like you wouldn't believe. Okay, so we've got the standard, we've got the code, but how does that code actually make a machine move? Well, it's all about this constant, super fast cycle of listening, thinking, and acting, and it happens faster than you can even blink. This right here is the absolute heart of how a PLC works. It's called the scan cycle. So first, it scans and reads all the inputs. Are any buttons pushed? Are the sensors triggered? Then it runs through your program, your ladder logic, from top to bottom. And finally, based on all that logic, it updates all the outputs. Turn on this motor, open that valve. And this whole thing, this entire cycle, happens in just a few milliseconds. It's crazy fast. And all of this is happening inside a physical box, which is usually a modular system. It's kind of like building with Legos. You start with the CPU, that's the brain, that snaps onto a rack which also holds the power supply. Then you start adding your input and output modules. Those are the physical connections to all the sensors and motors out on the factory floor. And finally, you've got communication ports to talk to other computers and control systems. And this kind of brings us full circle, right back to one of the biggest advantages of ladder logic. When a machine grinds to a halt, a technician can pull up the program on their laptop and literally see where the flow of logic is getting blocked. It's just like tracing the flow of power through a wire, which makes finding and fixing problems incredibly fast and intuitive. So we've come a long way, from these massive walls of clicking relays all the way to a global software standard. But the evolution is not over, not by a long shot. As we step into the era of Industry 4.0, with smart factories, AI, big data, it leaves us with one big question. Is this simple, visual language that was designed to replace old wires, is it powerful enough for our future? Or is the factory of tomorrow going to need to learn an entirely new language?